Okay, hi everyone. We are here to do a bit of Wolfram language design related to string diagrams. These are things that come up in lots of kinds of places to represent relationships between things where the relationships aren't just like ordinary graph relationships where it's just this is connected to that, but rather there are sort of definite named ports of some kind that are involved in those connections. And I was just
Yes.
playing around. Do you agree with that description?
Yep.
Yeah.
And I happen to have just been doing some things with lambda calculus, which is a case where you have that because you have in a lambda, you have both the bound variable and you have the body of the lambda. And those are two different kinds of things that have to be wired up. It's also the case, I mean, I don't know to what extent the head and arguments in our expressions can be thought of this way as well. Can you guys comment on that?
Yeah, you can.
Absolutely.
You can in fact like convert to diagram that we will discuss soon any expression, and it will do something meaningful.
Okay.
Perhaps.
All right, let's go ahead and install this packlet, and then
To elaborate a little bit, expressions are trees, and trees are a kind of string diagram.
Yes, but they're weird trees because they have heads, and when you draw them as a tree, I mean, if I were to make a random expression, you know, f of g of x, comma h of x, y, or something like this, and I were to say expression tree, the default tree that I'm going to get, oh, I see, it has these things as its nodes, right? But but the alternative, how do I get those things to kind of hang off on one side?
As a second argument, say atoms, and then also say heads goes to true. It's an option.
Right, so that there, I'm now got these sort of distinguished head-like things distinguished from the arguments.
Right.
Okay, let's dive in. Should we look at these examples?
Sure.
I still hate using the word diagram for these, but we'll worry about that later.
I'm hoping you'll warm up to it, but yeah.
I think last time you said that you're starting to like it. So.
What's that?
I think I heard you say you're starting to like it at some point.
Okay, fair enough. All right. Okay. So that's just a thing, and that thing could be like an image or anything, right?
Yes.
Could be anything.
So the data can be literally any expression.
Right. So just for fun.
Much like trees.
Yeah. Okay, there we go. Oops, doesn't fit. Well, so it goes. Okay.
Yeah, it's a fixed size graphics. Yeah.
Yeah, I understand, but it should have compressed itself. Just a minor bugette. Okay. Diagram with it. So the idea is that diagram has inputs and outputs. Is that right?
Yep.
Yes.
Diagram element of some kind. Okay. How do I, if in this syntax, if I wanted that input to be a list, I would have to go and I would have to say list A, correct?
Yep.
Okay. Convert to a string diagram. Right.
So this is showing what we were saying earlier, that trees are kind of a special case of string diagrams. You have many outputs, only one input.
I don't understand the labels on these.
Those are
just tree positions.
I see. Which in principle could also label these edges here. But no, these edges are dual to that. The elements here have tree positions. The edges are between two tree positions. Whereas here, I don't quite understand that. In what
The-
sense?
the-
I mean, you go ahead.
The edges on the string diagram are being labeled with the position of the thing that they are the input to.
Okay, which could also be done in a tree itself.
Yeah.
Okay.
This is just because with diagrams, the wire labels are shown by default.
Right.
And you specifically name the wires so that you can connect things in different ways.
What do you mean? I mean, because this is not using named ports, so presumably this thing here could be an association. Is that true?
Well, those are like there's a correspondence between the wires and the ports. These are port names or wire names.
Those are port names.
Yeah.
Yeah. The diagrams have input and output ports, but when you start to connecting those diagrams together, they become wires.
I see. And where the point is that that there are unique names for those ports, and the thing will assemble itself just like a graph assembles itself with nodes, uniquely named nodes, and every time you mention the node X, it means the same node.
Not quite. You can repeat port names
How?
across the diagram and even within a single box. I mean,
But I don't understand. How does it know what connects to what then?
That's controlled by the functions that you use to compose them, which we haven't seen
Okay,
yet.
we'll get to that.
But you could say like AAB for one of the lists of ports.
Right. Okay. So this,
perfectly fine.
I don't understand this. Yeah. This is saying, I don't understand this. Array.
This is showing a tensor contraction.
Yeah. I don't understand it. Explain it. A2. So
well, it's
why is it called A2?
Maybe this is like a little silly example because the actual contraction may be incorrect because the dimensions don't match. But you here just create for each symbolic array a diagram, and the dimensions would correspond to ports, right? And then all the compositions like array dots and transposes and Kronecker products should correspond to some kind of composition on the diagrams.
Yes, but I don't understand why this isn't right. I mean, so this is a matrix symbol that is being contracted. I don't really understand what this is. That's a matrix symbol.
I think the dimensions are reversed. The last one should start with 4.
Yeah, that's right.
Okay, yeah. And then it's a dot product.
Right.
Apparently, tensor diagram is happy to create a diagram even when the dimensions aren't.
Yeah, the problem is that arrays do not necessarily carry the information which port should correspond to input and output. So it's ambiguous where you put the port in and how to show the diagram. So it's a bit arbitrary right now.
Right, but I mean, a dot has a pretty definite, a dot is contracting from last index to first index.
Right.
Yeah.
But what Nick is saying is that
confused.
the indices aren't specified to be either input or output.
Okay, I'm totally confused. I thought matrix symbol that these things represented the dimensions of the matrix.
Yes.
Which has nothing to do with port names.
No,
I think they are trying to represent
port names. There's A1 and A2 are the port names.
Right. I think A1 is free. It means the first level of A.
I see.
And then the second level of A is constructed with the first level of B, and so the second and third levels of B are free.
But why is it going from B to A?
Yes, that's arbitrary. Mm-hmm.
But it's A2, and that could equally well be labeled B1.
Right.
Yeah.
And if I go and I say 3 here.
Well, matrix needs to.
You'd have to change matrix symbol to array symbol.
Okay. Then that's A3, which has nothing to do with these numbers, but it's A3 being that index there. that numbered index.
Yep.
Now, the reason I'm yakarating about, I mean, if we had named ports an array symbol, which we do not right now, right? If I say array symbol, you know, A, and then I start using something like this, that does
The
not
dimensions
work.
can be symbolic, right?
Yeah, they can be symbolic, but I can't do this. It's very confused there.
Mm-hmm.
Okay, but if can I represent a contraction on more than one index here? How do I do that?
Yeah, but the result may be very confusing. It's like, because you can try, but
Tensor contract, is that right?
yes.
There is also array dot, which may be simpler.
How does tensor contract work?
You have to do a tensor product first of the arrays.
I see. So why don't I use, what are you saying, array dot?
Yes, there is array dot. And then you specify how many levels you want to contract.
Oh, I see. No, but I want to do the, I mean, if I say tensor contract, and then I say tensor product.
Mm-hmm.
Okay, I'm not gonna guarantee that it will work, as you expect, but let's see.
Okay, so this now tensor contract then has in it a contraction,
right,
which says, what does it say?
Pairs. So you have now an object of 6 levels. So you can contract, for example, the second and the fifth.
2, 1, 3, 3. Let's try that.
No, free is like contract with itself. I think it doesn't work.
No, it doesn't, because isn't it from one tensor to the other? Oh, it's
No.
in the full tensor.
Exactly.
I get it. I get it.
Tensor contract only sees one tensor.
Right.
Right. So it's checking. So for example, here you can contract 2 and 5, which contain levels of dimension 3. And
Why
say,
can't I do 2 and 4?
Because it's 3 and 4.
It's 3 with 4. It's like dot. It will complain that you're contracting dimensions of. Right. So,
so
3 and 1
this has
also
dimension 6. This tensor product has dimension 6, right?
it has rank 6.
Rank 6.
And now you are contracting the second with the fifth, which is dimension 3, which is fine. But then also 3 with 1, which is 2 and 4. So do, for example, 3 and...
Let's just keep it simple.
Exactly. Yeah. Perfect.
Okay. This is really wild.
Yeah.
Okay, let's look at a simpler case. Let's just do one contraction.
And this is a potential connection with the port graphs project. There might be some layout algorithms that we could exploit here. So that
By the way, is this using your
goes
latest tech, Nick, for doing the layout?
No, this is just using graph layout. Here, just there are an explicit vertex for permutation, that one in the middle. That's the vertex diagram.
I see, but the stuff you were doing recently with resplining things and so on is not being used here.
Yeah, it's for different kind of compositions. This is like just making a tensor network. It's not like vertical, any like grid-like composition, so it's different.
Yeah. But let me see if I understand this. So this is saying these are loose indices, loose, tensor indices.
Yeah.
And these other tensor indices have been hooked up. I mean, it's a pretty crazy, circuitous route to hook them up.
Sort of, yeah. There's some ways to simplify it. It's like that.
Yes.
Yeah, the
you can
layout's
see what like
optimal.
simplified diagram does to this. Like there's a...
Yeah, they should look much before the previous case. Sorry, like the previous case.
That's nice.
Mm-hmm.
Okay, so let's understand what this is. So that means the B2 index which is that one there.
Yeah, the fifth.
Right, but I'm confused about why that label just confuses the heck out of me.
Well, I had
Because
to.
that,
I mean, it's
had to
also
name it the same.
A2, right?
yeah, right. It's also A2. So it would make more sense to me if this thing had, I mean, something like this is an A3, which is an unconnected A3 that could have, you know, a little extra line going out of it. But here it would make more sense if this said A2 on this side and B2 on this side.
There are many ways to parameterize it. Like you can insert an actual other diagram instead of wire that has different ports for the input and output, or you can just, like in this example, I just attach, like rename one of the ports so that they connect. It is just easier. It depends how the diagram constructed from the tensor. More or less.
Okay. So for example, if I take this diagram and I say, lovely. It's quite lovely. I mean, there's a lot of detail here which isn't quite right, but I mean, the basic structure is, I mean, like the fact that those cross over is, it's just because of a layout algorithm, right? There's no meaning to that crossover.
Yeah.
And the fact that this is going in this very complicated way, there's no meaning to that. It's just.
Yeah. Right now, just you put a vertex there and the layout doesn't know where the actual wires are coming from, so that's how it happens.
Right. Okay, I understand. So now can I go from this diagram back to some kind of expression?
You can
Diagram tensor.
do, for example,
That's pretty cool.
Yep.
Very nice. Okay. All right, quantum circuit. Let's see. Okay. So if I do this, and now I say diagram tensor of that. My God.
it will have some identities. Because diagram tensor might go through an extra step that turns it into a network with those unsimplified identity wires.
So there's identities there because this is a rectangular grid, and so it's putting explicit identities. And the other thing, I guess, is that this is using those shapes for different operators as the name of array symbols, right?
Yep. The rendering for the gate is just used as an expression, arbitrary expression.
Okay, but I mean, in this is various tensor symmetries here, right? Is that correct? No, that's a transposition. That's a transpose.
Right.
Can I do anything with this right now, or is it dead meat?
We can try to turn this one back to the diagram, but I suspect it's going to be very messy. A lot of wires. I think it's tensor diagram. Try. Exactly.
Pretty wiry. Okay. And now if I say,
but in theory, this is still equivalent.
Yeah, I'm not sure about the labeling of wires there. I know what happened, but yeah. Yeah, what simplifying does is basically tries to remove all the pure wires, the diagrams that are considered wires, like permutations and identity out from the network, and reconnect ports backward.
I see. Okay. Let's look at a lambda.
We probably have a local thing messing up some styles, but okay.
Do I probably have to quit this. Shall I quit the local lambdas thing?
Maybe not. If you do the Packlet install of Wolfram Lambda and you run this example, maybe it should work.
Okay.
Or we can just ignore just the lambda weird styles.
I'm just going to do Wolfram Lambda force version install, right?
Hold on. I was thinking about just the Packlet install of Wolfram / lambda from the repository.
I just did that. Yeah, I'm just saying force version install.
Okay, then.
For that. Okay. Okay, whatever. Minor baguette. My God. This business about these things getting rotated is kind of annoying. I mean, I do think that would be, well, I see, because it has to connect in the right place on the box. And that curlicue is amusing. So if I say random size lambda 10 or something, there's a lambda, and then I say toDiagram. Boy, that's a funky creature. So I see there's a bunch of compositions there. And that is a copy operation. Is that correct?
Right. This one specifically uses like 6 versions of the argument. So you have 6 outgoing wires from there.
So if I were to think about a diagram, I mean, it's sort of showing the flow of data. And it's showing it, I mean, in other words, if I were building a computer, this would be literally wires with data flowing through them. Is that true?
In this lambda case, I think it's not. It just shows, well, if you think of the creation of variable, is it just like a special wire type that starts flowing in backwards, which is very weird. It's not really showing the flow of the data.
Why are you saying that? I mean, this is a copy, right?
Well, maybe parts of it is just like not clear how to interpret the binding of variables in this case and how the variable is being substituted. It's not showing that at all.
So just to get some sense.
So we don't have an example in this notebook, but one thing you can do is take things from System Modeler and do toDiagram on it. So to the extent that you could represent like electronic circuits, you could convert those to string diagrams.
Can I try one? I mean, if I get one, let's just do it.
No, I didn't. I don't actually guarantee it. It's like there's some icons gonna be messy. Last time I tried it.
In principle, it should work. The implementation might not fully be there.
This is such a horrendous way of doing this, but this is what we have right now.
It has to be like a very simple example though, because it will try to convert all the diagrams and sub-diagrams, and there may be a lot of them.
Let's
you want to try a small example?
Let's try educational examples. Let's try electrical engineering. Should I try something like this?
Sure.
Oh no. Just happened here.
It's just like this one node can contain like a lot of hidden sub-diagrams.
What about neural nets? Do we have that as well? So if I say toDiagram of this.
There's at least a prototype implementation of converting neural nets to string diagrams using toDiagram.
Yeah.
Nick would have to speak to how complete the implementation is.
Though it's still messy. It may be less messy than the system modeler.
This may be horrendous.
there's like less dependency. There's actual, the graph is what you get already. You don't see. Yeah, I expect it like gonna be just a mess if it ever produces anything.
Fair enough. But in principle, that will work. And I mean, basically, okay, what's the relationship between? Oh, well, let's let it run while we chat. What's the relationship between diagrams and expressions?
Well, expressions are trees, and you can make a diagram corresponding to a tree.
Yeah, I understand. Right. But the diagrams are more general than expressions, is what you're saying. Although everything can be, obviously everything, these diagrams are expressions at some level, but in the same sense that a graph is sort of more general than an expression because it can be more than just a tree, so is a diagram. But a diagram, yeah, go ahead.
If we set aside for a second what Nick calls diagram network, which involves these like spiders, which kind of makes it into a hypergraph, the simplest form of string diagrams, the extra freedom you get is multiple inputs, not just multiple outputs.
For what? Sorry.
So like an expression, you could take a head and you can wire in arguments to it. This is something where you could wire in essentially multiple heads as well.
Let me understand that. I'm going to kill this.
I think the expression is mostly the output is single, right? If you want to make a diagram out of the expressions, the output is what's single, but diagram can contain multiple outputs.
Right. Right. You know, maybe there's something wrong with interrupting my computer because it never seems to work. How could there be something wrong with that?
Hello.
Hi.
Oh, it did abort, but it gave some weird thing. Okay, well, no matter. Okay, so I want to understand this point about relationship. Roger, we're talking about diagrams, as you can see, and we've got lots of different diagrams here and tensor diagrams and so on.
Actually, I think the next section of examples might clarify exactly the thing you're wondering.
Okay.
Sorry, the one after this. But these are special, like named diagrams that are very often useful.
So why is the copy diagram not what's used in the lambdas case? There.
This is just a copy to 2 currently.
Yeah.
I see. So there's iconography for that. That's a copy to any number, which happens to show up.
Maybe there should be a parameter for how many copies to make, and then it could be used there.
Right.
Well, in this case, it's rather like I not use the built-in copy diagram for lambda constructions.
Although in principle you could use that. Is that true?
Yes. Yep.
Yeah.
Okay.
Are these special things for tensor diagrams? The things that those 2 subsections there?
No,
string diagrams generally, and tensor diagrams is
tensor diagrams is a special case, right? So here we've got, you weren't here earlier, but I mean we've got a contraction here, right, of a tensor product like this.
I mean, it's probably like the most important special case.
So then it's a simplified diagram, and then presumably we can take that simplified diagram and say diagram tensor. Is that true? Of that, and we get that. That makes sense, Roger?
Oh, so that's another function that's its role to
convert diagrams to tensors.
Okay.
I mean, I think this is confusing here. The way
that diagram that's special, right? It's not just a ported graph. It's something tensorish.
Correct.
Okay, fine. Then it makes perfect sense.
Yeah.
Because yeah.
Well, it's not special. It doesn't have any special tensor components. It's just, as you said, graph with ports. But you can interpret all the wires.
But you don't want tensors out of diagrams. Why would you want that in general? Like that makes no sense. Like system modeler doesn't have tensors. Like You know, a million other diagrams don't have tensors. That's just a particular view.
Roger, you're missing the point. The whole point is this is a general way of doing diagrammatic computation. One particular representation of diagrams that's sometimes useful is a tensor representation.
Mm-hmm.
Okay.
I mean, I don't know what's
general. These are not quotes tensor diagrams. These are string diagrams in general.
What's general about it?
Okay, you weren't here at the beginning. I'm sorry.
Okay. I just feel that someone has looked at one particular case and they claim it's general.
That's not correct. If you'd been here at the beginning, you would have known that.
Hmm.
I mean, we've at least got quantum circuits. We've got Lambda calculus. We've got system modeler, although this conversion didn't work in this case, but in principle it works. And, you know, would you like to compare, guys, ported graphs versus this? I mean, to me, these things in a sense have values, whereas ported graphs no more have values than graphs have values. Is that a fair characterization?
What do you mean by values?
I could imagine turning one of these things into the number 3 or something. In other words, if I had these lambdas and I applied them to something or whatever else, I could imagine, you know, doing reduction of these lambdas, let's say beta reduction of the lambdas, and, you know, getting out some result.
Oh yeah, it's more like diagram equivalence. It's a bit more complicated than that. But yeah, you can imagine that if we had some particular theory of how diagrams can be written, then we can say which diagrams are equivalent under those rewriting rules. And then you can say that, yeah, maybe diagram corresponding to number 3 is the same as this.
Yes. Okay, let's keep going.
So this is the section I was saying might clarify what the relation is with expressions. We get two types of composition, vertical and horizontal, or you could say series and parallel.
What's diagram right composition?
Just in reverse order.
It composes them left to right rather than right to left. So that means first the A, then the B.
Oh, this has B first and then that. This composition is like applying this function first and then this function.
Exactly. This follows the convention of composition and right composition.
Right, but like graphs, what's happening is that the named wires are being matched up. Correct?
Yep.
So if there were two B wires, what would it do? I mean, if these diagrams, if I had, for example, here, if I said diagram, you know, let's say C, and then that one had, you know, B, comma, C, let's say. And then I took this and I said,
well, it wants to have a C input because that's the output of the other one.
no, but this is, if I do diagram composition of %69, comma, this thing, right? I
Should
first
just
apply.
Either the first, yeah. Just
Nice. Yeah.
So it picks the first B to fill with that. Is it obvious why it picks?
Well, it does them in order.
Okay.
Yeah.
A lot of languages have, you know, something that says what connects to what, basically. And that's why you want the ports names.
Yeah.
Like programming languages have that.
Well, what, in variables? Names of variables or what?
Yeah. So you have input variables, and then inside of a block, you give names and they connect to each other.
Right. Okay. So parallel composition. So this is like the whole monoidal category craziness. By the way, I assume these diagrams can also be used for category theory. Is that true?
Sure, yes.
So like from a theoretical perspective, string diagrams are representing morphisms in a monoidal category. Morphisms because you can connect them one after the other, and monoidal because you have a tensor product.
Right.
From a physical point of view, these are often called like process theories, where the wires represent systems and the boxes are like processes that act on those systems.
Yep. Okay, so this is a diagram product, which is the A and B together like that. And then the composition of that connects B to C. Yeah, okay, I get it. Okay, yep.
Are there, when you do it like this, are there sort of weird capture things that can happen? Like if that diagram product, let's say that it does have B's and twice. Oh.
Diagram
Basically,
product is just going to set things next to each other. It's not going to it's never going to wire words together.
But I'm just thinking of, let's say that the outputs for that second one was also B. What would happen type thing?
Well, we can try it. Output from which second one? This
Yeah,
one
the B system, the one that's sort of B in the...
So it's B.
You can wrap that diagram in the head diagram to override its ports. So just in place, do diagram open bracket.
Or you can click on the label. It will copy the minimal diagram constructor.
Click on which label? This one.
On the B label. You click it and paste it instead of that diagram. Right? It's kind of this representation.
I don't think this is easier personally.
Okay, but you do this then, right? So now I put that in here and then run it.
Oh.
So this introduced an identity. The B from the A went into the B of the C, and the B from the capital B. Oh no, it's the other way around. The B from the A is just loose.
Right.
Yeah.
Why did it?
And yeah, this is needlessly complicated with the crossings.
Yeah, the fact that it's like shows this outer ports now is because they don't actually match the inner ports that.
No, I got that. Okay, they have to be pulled out, but it made some choice here. Like,
yeah, that's right.
I think it was similar to that choice it was making earlier here, of which, well, it was somewhere back here, of connecting to the first one, right? In this case here, right? It connected to the first B.
Mm-hmm.
Okay. All right, so permutation is a common thing. By the way, Nick, do you have, I mean, the technology you just developed in the last few days that has dekinking in it? Is that, can I apply that to this, or is that not ready yet?
Well, you can, it's just somewhere, or you can pull it off from that notebook with string diagrams of lambdas.
You want, by the way, in this example, you want the crossings.
No, I understand. I'm just going to show you
X and Y, but you want the overall output to be Y and X.
The whole point is that Nick developed this dekinking mechanism using splines, right? Nick is using splines.
Yeah, it's just simple, like take the graphics, find all the disconnected lines, connect them, and smooth them out, right?
Right. So, for example, this is a lambda that's been dekinked.
No, this one is not dekinked. It's just.
Well, how about in here? If I'm looking at a bunch of lambdas, are these?
There's some that seem to take an extra little loop somewhere. I saw one just to.
Yeah.
Okay.
I mean, have these been dekinked or not?
No, I don't think so. This is how this thing will render it by default.
Okay, but I think this one has been dekinked.
Yeah, somewhat, right?
I mean, I know it's not perfect by any means. Okay. But so if these blocks represent actual functions, like, square a number or something, how do I deal with that? How do I make it resolve using that?
So I'll just say they don't have to represent functions. These could be even like relations, but I think there's a diagram. I think there's a diagram function. Okay, so the simplest string diagrams are the monoidal category case. You have vertical composition, horizontal composition.
Yes.
This is a different beast, which is a third type of composition where you introduce these things. They're called spiders.
Yes.
I guess because they look like spiders, but they're basically hyperedges. And here you don't have that hierarchy of horizontal, vertical.
Right. It's a hyperedge that is it's like a copy connector. Is that right? Which can copy.
Yeah.
Right.
Yeah. If the port used more than twice, it will create that.
And diagram network is what's being used by the Lambda diagrams.
Because they have those copies in them.
Right.
Mm-hmm.
So it's either relating to Roger's question, either you're picking just one C to make the connection, or in this case, you're
everything.
What's that?
This grabs all of the loose C's and connects them all
actually,
together.
this was what I was expecting to happen with the other example.
Yeah,
but I didn't know what semantic you had picked, so that's why I was asking.
But so for this is just a third type of composition that you can do.
Mm-hmm.
But you can convert back and forth. Like you can turn this into the grid-like monoidal composition.
I didn't have an example of this, but do diagram arrange.
This?
Or maybe it's or maybe it's a range diagram.
Diagram arrange.
Okay. This turned it into a bunch of horizontal and vertical compositions in a non-unique way, introducing caps.
I mean, it's basically a layout. It's what we might have called, graph layout or something.
It's basically layered. You took the graph and some foliation of it and turned it into products, each slice, and composed them.
It's not purely graphical layout. It introduced additional nodes so that this could be rectangularly built up using vertical and horizontal compositions.
What additional nodes?
For example, in the top right, in the top right corner, look in the very top right corner. There's a cap, or I guess that's a cup. It introduced that.
Not a node.
It is.
Well, it's not introduced. Maybe it introduced for rendering purposes, but the actual underlying diagram doesn't have it.
It doesn't have, but
it's one of those special diagrams. It's a cup diagram. It represents a bend in a wire.
Yes, but I mean, it's just a wire. This is the same. Oh, these arrows both come out.
Right. That's why it's a special diagram. Some process theories you're able to do this with, where you have a special box that acts like a wire, and then there's these like graphical deformations you can do, like a cap and a cup connected together. You can deform them into an identity.
Okay. All right. So let's go back up. You've got a bunch of types of. Okay, how would these be used for Feynman diagrams?
The interactions would be just these nodes with ports, right? And particles would be ports and wires.
Although in a Feynman diagram, the order of coming into a vertex, the order of edges doesn't matter.
Sure, you can ignore the direction of ports, so to speak. But you sort of have to pick up the foliation when you create the diagram, which direction you compose in it. But then you can just style it out how we want.
Right. Okay. Well, so what, I mean, this is all very interesting. I mean, how does it relate to, if I take an expression, that one that I had wherever it was, the f of g of whatever, this one here, can I make a diagram out of that?
Do two diagram of that tree.
Of
No,
the tree?
you don't even have to make a tree, just two diagram of the expression. It's the same as lambdas, just without special lambda heads.
Okay, now they're triangular things. What's the triangular stuff about?
Not just the shape of all the atoms, I guess. Maybe not the best one. I don't think there's anything to simplify there. You can arrange it.
For comparison, do two diagram of the tree.
Okay, but this diagram arrange.
Mm-hmm.
Yeah.
That's cool.
Diagram arrange converts from the diagram networks into grids of.
Okay, this helps me understand what's
N.
going on, right? Because this is basically showing how you compute f of g of x, blah, 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 just like the tree would show you how to compute it.
Yeah.
But now I don't understand these nodes. Oh, I see. This is a node.
It's just application, basically, or construct.
Right, although bizarrely, it has the head on the right, which is kind of unfortunate. I mean, for our purposes, construct should have the head on the left.
Stephen, can you please do two diagram of the tree alongside this so we can look at both?
Of this tree here?
Yes. Yep.
Or maybe you can try those new reflections. We can flip it, reverse it. I think it's a good example.
This thing here?
Yeah. You can diagram flip it.
Okay, now it looks a lot more like the tree.
And then do diagram reverse.
Okay, but the GH is sort of the wrong amount here.
That hence do diagram reverse.
Yeah, that will fix it.
There you go.
I see. That's pretty nice. So, I mean, as a way to understand and explain this, I mean, I don't really understand why the atoms are triangles here. What are the different kinds of things? There are boxes.
But it's just shapes. Those are arbitrary shapes for the diagram object. It's like a pure node without any further hierarchical structure. You can pick any shape or graphics for it.
Okay, that's fine. But I mean, the default. Right, but what are the. Okay, so that's just a node. But then there are these special copy nodes or constructor nodes. No, that's an application node as opposed to the copy node, right?
Yeah. Well, those are explicitly created when in the two diagram that took an expression and created all these nodes to connect with, right?
But this type of node is somehow special. It's not one of the general tensor box nodes.
It's not special. I think in this case, it's just a diagram that is rendered as this circle. Because when I took the expression, I had to somehow represent the creation of all the sub-expressions with construct.
But, okay, so you could as well have made this a box. And this,
Yes.
if I thought about this as a tensor, I don't quite understand what it is. Could I think of this as a tensor?
Well, you can think of any diagram as a tensor. If you just
You can do diagram tensor and you'll get something, whether it's meaningful. It's another question.
Yeah.
My God. That's pretty wild. the hell is that thing there?
Those are those application nodes.
That we're dotting on axis 3 with rank 4 application node. Is that right?
Yep.
Is that what that is?
Yep.
Is that array dot, or what is it, those dots?
Yeah, it's an array dot.
Oh, okay.
I think that means contracting 3 levels, not contracting level 3.
Exactly. It means, 3 levels, and the other one contracts 5 levels, the last 5, or the first one and first 5, or the last one.
So it's basically eating each one of these things from the tensor product.
Right.
Yeah, 1, 2, 3. Are they, how deep? Yeah, they're vectors. Yeah, so all of them, yeah.
It's eating those. This is very interesting. I mean, this is really quite unifying of a whole bunch of different kinds of approaches. I'm just trying to understand, when we compute from this, what do we expect the computations to look like?
So I think the two main computations that people do with string diagrams are deformations, which is like bending wires, reducing things to the identity.
Okay.
The other one is diagram substitution. You have some sub-diagram, you can expand it out or reduce it down to another equivalent diagram.
Okay, but what about evaluation of, that tensor, that f, for example, evaluates to 13 or something? What about that kind of thing?
So we have diagram function for that.
What does it do?
It converts a diagram into a pure function where
like tensors.
I think the input is in the form of an association. I'm not sure.
Oh, it's just
it's just a sequence.
It may be a sequence, maybe. It depends on what you want as an output.
Those dots are pretty weird.
Right.
I mean, this is pretty weird. I would expect this to ultimately...
Well, it's because this isn't really a diagram representing a function.
It's a diagram representing an expression.
Yeah. If the boxes had been things like a +2 function or a add function, sum, then you would have gotten a more meaningful function.
So if I say something like x squared plus 2x plus 7, and then I say 2 diagram of this.
Oh, that would treat it as an expression. All right.
A simple case: do diagram of plus, comma, list xy, comma z.
Okay.
And then do diagram function on that.
Okay, that's well and good.
I guess it was smart enough to simplify it.
Let me put a times. Let me put a plus. How do I put these together? So I'm putting this.
Replace plus with like slot 1 plus slot 2 ampersand. And make another one that's like a single input, then it is like slot 1 squared.
Okay.
Commas. So yeah, comma z.
Why do I have to? Okay, z, comma w or something.
Yeah.
Okay, now I say diagram composition of this guy.
Right.
And I say diagram function. Okay.
And then you can apply that to arguments. You could apply that whole thing to like 2, 3.
It may not be the actual function because the proper way to do it is like because the expression is not treated as a function. Yeah, it's that.
Oh, there's hold forms.
Yes. You need to annotate the expression with function. I think that's the way it works.
That's unfortunate.
Oh, we should understand this better. Okay. We should wrap up soon, but this is quite wonderful. This is quite, I mean, honestly, this is very helpful to me, at least, to understand what the heck these diagrams, you know, we've seen these diagrams in all these different places, and this is a really interesting unification and an interesting, I mean, I think there's more connections here. I don't know, Roger, would you like to comment on this?
Yeah, I don't think I've seen them the way you see them. So in most cases where, actually I've seen some of this too, now that I think about it. But most cases where I see them, you make sort of explicit wires. They don't automatically happen, so to speak.
Okay.
You know, and
so when you make a diagram, you are making it more like a graph, where you're explicitly adding edges.
Yeah. So that's how circuits work, you know, like even VHDL, which is digital circuit stuff, you know, like that language. And that's, you know, you have to pick to say where you know, connect a wire, you have to say component and port, basically, in some way, you know, like what's the box and what's the port. Because, yeah.
So Roger, years ago, you studied diagrammatic things, and you didn't convince me that we should build it at that time, but I think you'd inventoried lots of different types of diagrams. Is that true?
Yeah. So, I mean, I call them graph languages. So people use graphs to represent lots of things, like circuits but
maybe
UML
maybe you could dust
diagrams.
off that what you studied there.
I can, yes. Yeah. Yeah. You know, and so so there's a huge the one thing to remember, there's a huge difference of having just a diagram and also have the compute backend for it.
Yeah.
So sometimes it might be enough to have the diagram because you want to communicate something. So we could clearly support way more graphs, diagrams, if you like, than backends. You know,
right. Although the backend,
like say that represented VHDL, then we would have to have a VHDL simulator or a Verilog simulator, and that's like itself a tall order.
Right, but it's like an expression. Look, this is a generalization of expressions, basically. And, you know, like in category theory, the expression is the, you know, the structure of the expression is the payload, so to speak.
Right.
In lambda calculus, you know, there is a reduction operation. In tensor algebra, I guess.
But
I think what people primarily use string diagrams for is it's a graphical way of doing algebraic simplifications, which is the stuff about bending wires and doing diagram substitution.
You know, in a lot of contexts, you know, in order to hide abstractions, you know, like think of an integrated circuit that has, let's say, 50 billion components. You can't look at them all. So people use hierarchies. They say, this is an arithmetic logic unit, or this is a register, you know, so you get higher and higher levels of abstraction. So they're not so directly they're not flat like you guys. Do you know what I'm saying?
It's not really flat either. You can have diagram inside diagram. It's hierarchical.
You can? Okay. Cool.
Yes.
Yeah, because that's, you know, wherever I look, that's turned out to be like a system modeler. That's absolutely crucial. If you made it all flat, it would be very complex. And, you know, you can imagine, as I said, a modern integrated circuit. We can still do it. It's just you can't do it all flat. Just like impossible to understand.
Right. Right. So that's a different thing, is the hierarchicalization of these diagrams, which didn't quite do what I expected there. But
the hierarchy is, you know, by the time you have ports, hierarchies makes a whole lot more sense. And it's the same as kind of, you know, structured programming, basically. You know, where you have sub procedures and things like that.
Can you wrap with that in a diagram you just tried with singleton diagram? Because it's like
a diagram here.
Yeah, like singleton diagram.
The symbol singleton diagram.
It's like a wrapper so that it's not just overwriting ports, but like make this new diagram, which is just the diagram. Okay, maybe.
Okay.
That didn't work as expected.
So, I mean, but in tensors, for example, tensor contraction identities, like, random identities about the Riemann tensor, those can be represented using these diagrams, right?
Yeah.
Yeah.
As can a bunch of
that's
stuff
the algebraic manipulations that I was talking about.
Right. As can a bunch of stuff in group theory and so on.
Mm-hmm. Like, for example, a trace is like a loop of one of these boxes having its output wire wired to its input.
Right. Okay. So the other big thing here is the relation to graphs with ports. So I think the next in this series of meetings better include Charles, and we better talk about graphs with ports and how it relates to this.
Mm-hmm.
I mean, my feeling is there's a special case of graphs with ports with a bunch of extra semantics.
That's what I think too.
I agree.
But very useful semantics, but which
I
repeatedly in many many different cases.
Yeah, if I didn't mean to sound critical. The specializations are super useful. Not at all bad. Yeah.
Right. But I mean, this will allow us to do many of the things that we've wanted to do with graphs with ports, we would already be able to do with this, like neural nets, like quantum circuits, bunch of things, like process algebra. Very nice.
Yep.
Okay, I gotta go, but to be continued. And I think next time, now that I get some basic lay of the land, I think, among the things to think about are, just how sophisticated can we get these layout algorithms to be? And also, as we inventory these different areas, whether it's category theory, whether it's quantum circuits and so on, and as Roger points out, part of it's just like you can have an arbitrary expression that's just generic symbolic stuff, or you can have an expression that means something with polynomials or something like this. So I think you guys have started enumerating, the meaningful versions of diagrams. Let's continue that and try and understand, for example, category theory may be easy for us to now, have a thing, a morphism object and things like this. Is that a fair guess?
Yeah, I mean these are at some level they're morphisms in a monoidal category.
Indeed, but that's why I'm saying that maybe we then need to have, we need to understand what are the domains in which we will have, domain-specific wrappers around this mechanism, so that we can both start building those wrappers and start checking that this formalism, covers all the things we need for those wrappers. That
Understood.
Reasonable?
Yep.
This is very nice. Good stuff. All right, I'm gonna run. See, and it would be good if you guys talk to Charles and try and understand something. Make sure he understands this. You can listen to this recording and go from there.
Yep.
All right. See you guys soon.